AP Statistics, we're starting chapter 10 today, and now it's going to be on two sample data. Two sample. Imagine this. I've given this kind of example before, I'm sure, but we want to take a guess at not just the intelligence with IQ scores of the very fine Keeneland High School students, but also the losers over there in Sycamore. You see what I mean? Like, there's no way they're smarter than us. So I can't just take a random sample of Keeneland and Sycamore kids and try and figure that out. That doesn't make any sense. And I damn sure shouldn't like randomly pick a Keeneland student and randomly pick a Sycamore student and then just combine those two and then have a whole bunch of pairs, because they, how would a kid pair up versus a kid? Like, that doesn't make sense unless we actually went and picked our smartest kid and their smartest kid and our dumbest kid and their dumbest kid, and we kind of try to compare them that way. What would be better is to take a random sample of 100 Keeneland students and call it sample number 1, and take a random sample of 100 of these morons here and call that sample number 2, and make 2 samples so that we could get 2 X bars. Now let's compare 2 statistics. That's what we're going to do in chapter 10. We will do confidence intervals for subtracting X bars. We will do confidence intervals for subtracting proportions. We will do a significance test for subtracting X bars, and we will do a significance test for subtracting proportions. And that's it. That's all of chapter 10 in one sentence. Okay, here's where we start. Instead of using inference for P, the population proportion, using P hat that I calculate from one sample data, what I'm going to do in chapter 10 is I'm going to do some inference for P1 minus P2, if I'm using proportions and not means, using a P1 hat minus P2 hat from 2 samples, right? What's the percentage of Keeneland students that drive for over 20 minutes to get to school versus the percentage of Sycamore students who drive for over 20 minutes to school? I would take 2 samples, get 2 P hats, and I would subtract them. Here's a little review. This right here comes to you from your buddy chapter 7. Remember that retake is almost up. Describing the sampling distribution of P hat just by itself. This is chapter 7. This is one sample data stuff. The center, the mean of the sampling distribution of P hat is always this. Mean of P hat equals the population proportion. The standard deviation, which I will abbreviate because I'm tired of writing that phrase at this point of the year. The standard deviation of P hat is sigma of P hat was equal to, you remember it, P times Q over N. We changed that up and called it a standard error in practice to do a confidence interval or a significance test, but as far as the standard deviation theory, it was just square root of PQ over N. The shape, well, P hat is approximately normal if N times P is greater than or equal to 10, and N times Q is also greater than or equal to 10. That's what we know from chapter 7, so let's describe the sampling distribution, shall we? Let's describe the sampling distribution of P1 hat minus P2 hat coming from 2 separate samples to give me 2 separate P hats. What would that sampling distribution look like? Is it a normal curve? What's the mean? What's the standard deviation so that I can make a confidence interval or do a significance test? From sample 1, the mean of the P hats, mean of P hat 1 would just be population proportion 1. The mean of P hat 2, oops, wrote a 1 instead of a 2, that would be the population proportion 2. Now, the standard deviation for P hat 1 and the standard deviation for P hat 2. This, of course, would be the square root of P1 Q1 over N1. And this would be P2 Q2 over N2. Coming from 2 different samples from 2 different populations, now I got to call them P1, P2, Q1, Q2, N1, N2. I think that should make sense. But now let's put them together with subtraction. And you learned in chapter 6, I'm pretty sure chapter 6, you learned that when you subtract 2 entire distributions, you just subtract their means. I know you learned that. It looked like this back in the day. You don't have to write this in your notes, but from chapter 6, if you want the x minus y distribution, the mean of x minus y was just simply equal to the mean of x minus the mean of y. You were allowed to just subtract the means. So the center of the p1 hat minus p2 hat sampling distribution is just mu of p1 hat minus p2 hat. My new mean for this difference is just p1 minus p2. That's my new mean. I just found the center of my distribution. Let's go to page 2. I think you guys are going to find that this chapter is pretty easy. It's going to be very repetitive of stuff you've learned before. Now, when exactly do you add or subtract standard deviations? The answer to that is never. It has been decreed. It has thusly been decreed in this classroom that you never, ever, ever add or subtract standard deviations. The math doesn't support it. The pattern doesn't support it. But what you do is you square them, add them as variances, which is why we had to learn that word in chapter 1 in the first place, then take the square root. You learned, again, I'll put it in another little thought bubble up here, you learned that the standard deviation of x minus y was the square root of the standard deviation of x squared plus the standard deviation of y squared, right? If the standard deviation of p1 hat is the square root of p1 q1 over n1, which I wrote on the last page, and the standard deviation of p2 hat is the square root of p2 q2 over n2. If those two things are true, and I'm looking for a standard deviation of p1 hat minus p2 hat, I got to square them so the square roots go away, add these two fractions, and put a big ass square root over the whole thing. So it's going to go like this. Sigma of p1 hat minus p2 hat has to be equal to the square root of sigma of p1 hat squared plus sigma of p hat 2 squared. Remember, you always add them. Whether you're adding or subtracting, you always add them. That was a quirky thing in that chapter. Or it's going to go like this. Here it is. It's the square root of. This thing squared will be p1 q1 over n1 with no immediate little square root over it. And then this one squared will be p2 q2 over n2. All right, there's your standard deviation. I have now found the center of my new distribution, and I found the standard deviation of my new distribution. Let's talk about the shape. We learned in chapter 6 that if two distributions that I want to put together are both normally distributed, if I got two normal distributions, a new distribution created by adding or subtracting will also be normal. You learned that in chapter 6. You took a test on it. You got it right. Most of you. Okay. So what I'm saying is, if I know that the p1 hat distribution is normal, and I know that the p2 hat distribution is normal, when I put them together, my new distribution will also be normal. So look, p1 hat minus p2 hat, that difference of proportions is approximately normal if all of these are greater than or equal to 10. And you know where I'm going with this. You know what they are. Ready? N1 times P1, N1 times Q1, N2 times P2, and N2 times Q2. I got two samples now, so I got to check the N times P and N times Q for both of them. If they're all bigger than 10, both individual distributions are normal, so when I subtract them, my difference would be normal. So here's a summary. This whole thing down here, this is my summary. This is the sampling distribution for P1 hat minus P2 hat. This whole thing. So what if I was writing this statistics book and if I wanted to change something, when I got done with chapter 7, where we had a sampling distribution for P hat and X bar, I would have pushed you a little further and come up with a sampling distribution for what happens when I subtract them, so that when we got to this point of this chapter, we'd be ready to go. But that sampling distribution, chapter 7, when you first come across it, it's a bit tough. So maybe they did it right. The sampling distribution for P1 hat minus P2 hat goes like this. The center, the mean of P1 hat minus P2 hat, you're going to get tired of writing that, is equal to P1 minus P2. If you have the same kind of intelligence at Sycamore, doubt it, that you have at Caneland, then when I subtract these, I should get 0. The spread, sigma of P1 hat minus P2 hat. Sigma is equal to a big square root of P1 Q1 over N1 plus P2 Q2 over N2. And for such an intimidating looking formula, I think this should actually make pretty good sense to you guys. I think you should be looking at it and going, yeah, that is a scary looking formula, and yeah, I know what it means. It's approximately normal if N1 P1, N1 Q1, N2 P2, and N2 Q2 are all greater than or equal to 10. That's my sampling distribution, just like we did in Chapter 7. And then my next step, Chapter 7 was sampling distribution, guys. Chapter 8 was confidence interval. So I'm going to do a confidence interval for an unknown difference of proportions between two populations. Let's go to page 3. So on page 3, I have you guys a goldfish example. You can read through that and fill that in. It's basically asking you to name the shape and the center and the spread, and you can read through it and put this in. So you can just copy my notes later on this. I think I'm going to keep moving on in the video, mostly because I got a lot to do tonight and I'd like to save a little bit of time. I don't even care if you're mad about that. The confidence interval, here it is. So now this was like chapter 8. So we just did chapter 7 stuff with 2 proportions. Now we're going to do chapter 8 stuff with 2 proportions. And tomorrow we're going to do a significance test. So that'll be chapter 9 stuff with 2 proportions. Here we go. This is called the 2-sample Z interval, or on your calculator, if you want to use your calculator for it, it's called a 2-proportion Z interval. It seems like this is how it should go. I'll put a big giant parentheses. It should go P1 hat minus P2 hat. I should subtract the 2 proportions I get from my 2 samples, and then I should go plus or minus Z star times a big square root of P1 Q1 over N1 plus P2 Q2 over N2. And I'll put parentheses there. That should be my formula. Point estimate plus or minus critical value times standard deviation. But we wouldn't know P1 or P2, which we would have to use right there. This is the same problem we ran into in chapter 8. So we're going to substitute P1 hat and P2 hat for the unknown P1 and P2 that we don't know, and we're going to put them right there, just like we did last time. And we will call the result the standard error, just like we did last time. It's a mistake, but it's going to be close enough that we can use it, and we'll do it the same way, making it a standard thing. So look, the standard error for P hat is equal to a big square root of P1 hat, Q1 hat over N1, and P2 hat, Q2 hat over N2. That's technically not the standard deviation of the sampling distribution. It's an error. We're always going to do it the same way to make it standard, and we're going to use it. We're going to use it in our confidence interval. So here it is, ladies and gentlemen, the confidence interval for estimating the difference between 2 population proportions. We are smack dab in the middle of chapter 10 now, people. Draw an SRS of size N1 from population 1 and calculate P1 hat. Do your work. You guys learned how to take an appropriate sample way back in chapter 4. You learned how to find P hats and sample sizes in chapter 1. Then draw a separate SRS of size N2 from population 2, Sycamore sucks, and calculate P2 hat. Right? Now I got 2 samples from 2 SRSs. I got 2 P hats, so I can make my confidence interval happen. Let's go. On the last page, I got a big old place to put this confidence interval. Here we go. The level C confidence interval for P1 minus P2. I want to estimate this is the difference in population proportions. Let's say we wanted to talk about the proportion of Caneland students who we would consider smart and nice people and good looking, and then we go to Sycamore and count the proportion of people who are smart and nice people and good looking. We would kill them, obviously. This percentage would be way higher than that one. So when we subtract it, it would be positive, wouldn't it? We're looking for the difference in population proportions. This is how you do your confidence interval. Look, I put a big opening parentheses, and I'll put a little one for P1 hat minus P2 hat. Subtract the percentage of Canelan students I get who are, what did I say, smart, nice, and good looking. Subtract the percentage of those kind of people from Sycamore. This will definitely be a positive number. And then go plus or minus Z star, and then be times the square root of, I'm supposed to go P1 Q1 over N1, but I got to use the standard error for this, so I'm going to hat those up, and I'll use the sample proportions in this for my standard error. And then P2 hat Q2 hat over N2, and I finish my parentheses. Ladies and gentlemen, there it is. What a beautiful piece of mathematical work right there. That is the 2 proportion Z interval. Conditions. I think these are going to look very familiar to you. The random condition. All right. The 2 samples come from 2 SRSs from the 2 populations of interest. So when you start this right up, you're not going to say our population of interest is. You're going to say our 2 populations of interest are students at Caneland and students at Sycamore. Right? We performed 2 simple random samples to get our 2 sample proportions, that kind of thing. Now the independent condition, we've got to put a little wrinkle in this, guys. The independent condition. First, the 2 groups being sampled must be independent from each other. What do I mean by that? Let's say we were at some kind of an event where there were Canelan students and Sycamore students, and it instead of being about intelligence or whatever, let's say it's a sporting event, and Sycamore goes first. Like we randomly pick kids and we have them do some kind of an athletic activity, and then they get a score, and then Canelan's up second. You know Canelan's about to try harder. You see what I mean? So the groups have to be independent of each other. If you have one group get sampled and they get to see the process, they might go through the process differently. So that's what I mean by they got to be independent from each other, as well as within each group. Now that's what we've been worried about. The within each group, that's got to be the 10% rule since we sample without replacement, right? So then the population 1 has to be greater than or equal to 10 times the sample size 1. And the population 2 has to be greater than or equal to 10 times the sample size 2. The populations don't have to be the same size. Canelan and Sycamore aren't the same size. And the samples don't even have to be the same size. I could take 100 here and 50 there. As long as I can prove both of them are normal for the normal condition, it doesn't matter. That's if you are sampling without replacement. Of course, we've talked about that before. And then number 3, you know what the third condition is? The normal condition. The normal condition says all of N1, now look what I'm going to do here for this because I put these in here. I'm going to say N1 times P1 hat, N1 times Q1 hat, N2 times P2 hat, and N2 times Q2 hat all have to be greater than or equal to 10. There's your conditions. So I'll tell you what, I'm not going to talk you through these. I think you should read through those. I'm going to give you a small amount of homework. I'll post it on Canvas. Or you guys could do the sapling one, but I mean, that's usually longer than we want, right? But read through these. The book's got the answers, so you can read through and see how they go. I feel like, I'm not in front of you guys talking, so I don't see if you're nodding your heads and agreeing with me or asking questions or whatever, but my experience tells me that you guys should be following along with this pretty okay. So if you read through those, I think you're going to be okay doing your homework. Prove me wrong. All right, have a good day, everybody. Bye.